What is stoichiometry? So stoichiometry is simply the branch of chemistry that deals with the quantitative relationships between reactants and products in a chemical reaction. Okay, so in this lesson today, we are going to discuss the relative masses of atoms and molecules. We are also going to discuss the determination of relative atomic masses from percentage composition. We are of course going to also discuss the empirical and molecular formula. That is for today's lesson. So let's begin with the relative masses of atoms and of course molecules. So what is a relative atomic mass? However, before I define what a relative atomic mass is, it is important that we know which symbol represents the atomic mass of whatever the compound or rather the element is given. So atomic mass or relative atomic mass is represented by this symbol. So whenever we see this symbol in chemistry, this represents our relative mass or rather atomic mass. So relative atomic mass, of course, is the weighted mean mass of an atom of an element compared with 1/12 of the mass of an atom of carbon-12. So take note, carbon-12 is used as the standard in this case, and all the masses are relative to this same carbon-12. The 1/12 of the mass of carbon is one mass unity. Okay, and then carbon-12 is the isotope of an atom that has 6 protons and 6 neutrons, and of course we are talking about carbon. Okay, so carbon-12 is defined as having a relative atomic mass of 12. So as we keep on going, you are going to understand what all these things are. So let's discuss the new term that has come in, the relative isotopic mass. Did you get that? Okay. So the relative isotopic mass is simply the mass of an atom of an isotope compared with 1/12 of the mass of an atom of carbon-12. For example, oxygen has the relative isotopic mass of what? Yeah, of 16. When we look at the periodic table, this is the isotopic mass of oxygen. So relative atomic mass are found in the periodic table. Okay, we know these relative atomic masses are found in the periodic table. These are the ones that the periodic table has, because each element on the periodic table has its relative atomic mass, just as the oxygen has 16. Now, why are these not whole numbers? Because when we look at the periodic table, we are going to see different figures with points. Why are they not written in whole numbers? Well, they are actually the average mass of all atoms of that element. That's why they are not whole numbers. And then why do we need an average instead of just the whole number? Well, elements have more than one naturally occurring isotope with different masses. For example, when we look at chlorine, there is chlorine 35.5, there is also chlorine 34.5, and also the 7. So there is chlorine 37. We also have chlorine 35.5. So chlorine occurs in two forms. So as we can see, chlorine has two mass values instead of one. That's why it is not just 30. For example, it has not just been written as 35, but instead it's written as 35.5 because this is an average value. So let's look at an example of a relative isotopic mass. But before we do that, it is wise that we discuss first the formula that we use for us to calculate the relative isotopic mass. So relative isotopic mass is calculated, so let's just represent this. Relative isotopic mass by RIM is calculated by multiplying the mass given of the element multiplied by the percentage over what? Over 100. So this is the formula that we use whenever we are calculating the relative isotopic mass. So let's have an example. Let's say we have chlorine. Okay, let's say we have chlorine having the relative mass of, let's say, 37, and then it has, let's say, the percentage of 24. 0.5%. And also chlorine. Okay, chlorine, that is, let's say this is chlorine 35. Let's say it has the percentage of 35, or rather 75.5. This is the percentage for this chlorine. So chlorine 35 is having this percentage, and chlorine 37 is having this percentage. What do you think could be the relative atomic, or rather could be the relative isotopic mass for this? So in the formula we had said that we multiply the mass multiplied by the what? The percentage. So we have two chlorine in this case. So the first one has the percentage, or rather the mass of 37. Okay, so let's multiply this with its percentage, which was what? Okay, it was 24.5. Okay, so this we are going to categorize it as that, and then we add it to another one, which of course had the mass of what? 35. So mass of 35 multiplied by the percentage for this was 75.5. okay, so all these should be divided by what? 100, as discussed earlier. So let's try to calculate these values. Okay, so remember there is a point here. Okay, so when we calculate that, we are having 906.5, okay, plus, so let's also multiply this value here. So 35 multiplied by 75.5, there is a point here as well. Okay, we are going to have 2642.5 as well, over 100. Okay, so let's just try to wrap the top part here, since we are done with the calculation there. So what are we going to have when we manipulate this on the calculator? So let's add 906 added to 2642.5. So we are going to have what? 3549 over what? Over 100. So when we divide this value, what are we going to have? When we divide by 100, of course we are going to have 35.49. so this value here is the value for the relative isotopic number. So this is actually how we calculate the relative isotopic mass number. So in this case we write 35.5. so this is basically the average that is found on the periodic table. So the values that are on the periodic table are averages. That's why they are in point form, because we calculate the average for us to have the value on the periodic table. So having discussed this, let's also discuss the relative molecular mass. What is the relative molecular mass? So the relative molecular mass is as well represented by capital letter M and small letter r, which of course we abbreviate as the Mr. So what is Mr.? Oh well, just joking. So the relative molecular mass is the weighted mean mass of a molecule compared with 1/12 of the mass of an atom of carbon 12. Well, this looks the same as the relative mass of atoms, right? Okay, so the difference between the relative atomic mass and the relative molecular mass is that relative atomic mass deals with what? Elements. So relative atomic mass deals with what? Elements. Okay, whilst the relative molecular mass deals with what? Compounds. So this is basically the difference between the two. So whenever you are dealing with a compound, it means that you should look for the what? Relative molecular mass. Whilst when you are dealing with the elements, you should look for what? For the relative atomic mass. This is the difference between the two. However, they are just calculated in the same way. It's just that they are used on different molecules. Okay, so now let's say for example we have ethane. Okay, let's say we have ethane, which is of course CH6 here, and then we have 2 there. What could be the relative molecular mass of this compound? So the addition of individual elements, okay, individual elements is what we call the relative molecular mass, whereas each individual element itself is the relative atomic mass. So in short, relative molecular mass is the summation of relative atomic mass. That's what we can say in short. So how can we add this? So we know that here hydrogen, okay, is 6 multiplied by its relative atomic number, which of course is 1, and then carbon likewise is twice multiplied by its relative atomic mass number of what? Of 12. So let's multiply that. So 6 multiplied by 1, it's simply 6, and then 2 multiplied by 12, it's simply 24. So when we add the two values, we are going to have 30. Okay, if you want, we can put also 0.0, or we just write 30. Okay, so 0.0. So this is the relative molecular mass number. Okay, so relative molecular mass is also called the molecular weight. Molecular weight abbreviated as MW. It's just the same thing. If you see this word relative, or rather molecular weight, it's just the same as relative mass number. So this is simply the sum of the atomic weights of the atoms in a molecule, as I have said before. Okay, so we can have a lot of examples. For example, if we have H2 and then we have been asked to calculate the relative atomic number, what do you think would be the value? The relative atomic number for this is simply 1. Okay, whereas its relative molecular mass number is what? Is twice this value here, which is 1. So it's twice the value that we have on the top. Of course it's 2. So this is the relative mass number, whereas this is the relative atomic number. That's the difference between the two. Let's look at another example. Let's say we have carbon monoxide, that is CO. So to calculate the relative atomic number, we are going to calculate the relative atomic number individually. Okay, so in this case we are going to have, for the carbon, of course we only have 1 here, so it's 1 multiplied by 12, and of course we are going to have what? 12. Okay, and then when we look at oxygen, it's also 1, so we are going to multiply it with what? 16. So we are going to have 16, and of course this is the answer. But if we have been asked to calculate the molecular mass of this compound, the carbon monoxide, we have to add these two. So of course we are going to have 12 plus 16, and this is going to give us what? Yeah, 28. Okay, so the units for this is AMU, which of course is simply the atomic mass unit. Okay, so this is basically how we calculate the relative atomic number and the relative molecular mass number. So having discussed that, let's also discuss the percentage composition. How do we calculate the percentage composition? So percentage composition of a compound is simply the relative measure of the mass of each different element present in the compound. So the percentage by mass can be calculated by, percentage by mass is simply calculated by mass of an element. So mass of element that we have, okay, over the mass of the compound, the whole compound. So mass of compound. Okay, so hopefully you are taking note of everything that's being said, so that you revise easily. Multiplied by 100%. Okay, so this is basically how we calculate the percentage by mass of the given compound. Now let's look at an example. Let's say we have been asked to calculate the percentage composition of water. How can we calculate that? So having discussed how we can find the relative atomic mass and also the relative mass number, this is gonna be easier for us, right? So for us to calculate the percentage composition of water, we first have to calculate their relative atomic numbers. So we have water is H2O, right? We know this. Okay, so for us to calculate the percentage composition, let's first calculate their relative mass numbers. So for hydrogen, we know we have H2 there, so we are going to multiply twice. The mass of hydrogen is what? Is 1. So in this case we have what? Okay, so is 1. However, in other periodic tables, it's written as 1.01. This is just the same. The saying of saying mass is 1 is simply the rounded value. However, as we have discussed before, we write the average values. So in this case, we have the mass of hydrogen being 1.01. When we multiply this by 2, of course, we are going to have 2.02. Okay, so this is the relative mass of what? Of hydrogen. Now, what is the relative atomic number for oxygen? So this is relative atomic, it's not relative mass because it's only 1. This is relative mass because they are what? 2 of them. That's the difference. So you are going to observe that on this one I was using the relative mass because they are 2, whilst on oxygen I'm going to use only 1, that is atomic mass. So in this, relative atomic mass for this is 1 multiplied by, okay, there was a point here, 1 multiplied by the mass number for oxygen is what? Is 15.99. Okay, in other periodic tables this is rounded to 16. Okay, so when we multiply this, of course we are just going to have 15.99. So these are individual values. Now, when we look at the formula, it says mass of an element over the mass of a compound. So the compound you have is the total of this. So in this case, for us to have the mass of the compound of the total of this, we have to add these values here. So how are we going to do that? So we are going to add 2.02. We are going to add to what? 15.99. So what is the value when we add the 2? So when we add the 2, of course we are going to have 18.02. So this is the total mass for what? For the compound of water. Now, for us to calculate the percentage composition, we have to calculate the percentage for each element, that is for hydrogen and also for oxygen. So let's keep this 18.02 aside. So remember, the formula is mass of the element over the mass of the compound multiplied by 100%. So let's begin with the percentage of what? Percentage of hydrogen. So what are we going to have as the percentage of hydrogen in this compound? So the mass of the element, remember, the mass of hydrogen we had calculated was what? 2.02, okay, over the mass of the compound, the total compound is what? 18.02. So now this has to be multiplied by 100%. So what are we going to have if we divide in there? So if we divide these two values, of course we are going to have 11.2%. So this implies that hydrogen is 11.2% in water. Now let's calculate the percentage of oxygen in water. What is the percentage of oxygen in water? So the percentage of oxygen in water, we know that the percentage of, or rather the mass of the element was 15.99, okay, for oxygen, and then the mass for the total compound is 18.02 grams. So we multiply this by what? 100%. Okay, so what are we going to have here? So we are going to have 0.8 also percentage composition of oxygen. So in this case, this implies that oxygen is much more of it than hydrogen in water. So we have a lot of oxygen in water than we have for hydrogen. So this is basically how we calculate the percentage composition. So remember, the mass of an element over the mass of the compound multiplied by the what? The 100%. So this is how we go about this. So now in this case, let's discuss the empirical and molecular formulas. How do we go about empirical and molecular formulas of different compounds? So what is an empirical formula, or what is empirical in short? So empirical is simply the simplest whole number ratio of atoms in a formula. So you are going to be given percentage composition by mass of different elements, just as we are from doing. It's not very much different. Okay, let's say for example we have been asked to determine the empirical formula of sulfur oxide. Now sulfur oxide, we know its original formula, right? But we are not going to write it. We are going to assume that we do not know its formula. Okay, so we have been asked to determine the empirical formula of sulfur oxide. That is determined to be, let's say 40%. Let's say there is 40% of sulfur and there is also 59.95% of what? Let's say of oxygen. Okay, so how can we calculate the empirical formula for this, for sulfur oxide? So the steps for us to calculate the empirical formula for this element here, we can simply begin by writing a table. However, there are many methods we can use. It's not only what I'm using, but however, this is just a simple way. So let's keep these values. We have 40% of sulfur. We also have 59.95% of oxygen. So make sure that we keep these values. Okay, so let's draw a table now. So we have this table here. So let's say here we have for sulfur, okay, and then here we have oxygen. So at first we have to calculate the what? The relative mass of these. So how do we calculate the relative mass of this? So in this case, we have been given the percentages. So the mass given is in percentage. So here we have to write the mass that is being given. And in this case, we have been given the mass to be in what? In percentage. So for sulfur we have 40, and for oxygen we have 59 point what? Okay, we have 59.95. After we are done with this, we have to write their relative atomic mass numbers. These are the values that are found on the periodic table. So now for sulfur we have 32 on the periodic table. Okay, we have 32.07. And of course for oxygen we have what? 15.99, or 16 as being rounded off in other books. So in this case, the next thing that we have to do here is dividing these values. So we have to divide this value divided by this, likewise this value divided by this. By the way, there is a point here. Okay, so this relative atomic mass, of course, we know is calculated in gram per mole. Okay, so let's do that. So let's divide. So we are going to divide 40, okay, divided by 32.07, okay, 07. Oh, sorry, my apologies for that. So 07. Okay, there is a point here. Even here we have 59.95 divided by what? 15 point, okay, 15.99. So let's divide these values so that we see what we are going to have. So what is 40 divided by 32.07? So 40 divided by 32.07, we are going to have, okay, we are going to have, let me just continue from here. So it's the continuation of the previous table. Okay, so we are going to have 1 point for, this is for sulfur, mind you. So we are going to have 249. Okay, and then for oxygen we are going to have 3.749. okay, so this side is for oxygen. Now when you are done with this part, the next thing that we have to do is divide the smallest number. So you have to divide the smallest value into the bigger value. So when we look at the 2, the smallest value is this one. So this is what's gonna be divided into both sides. So we are going to have 1.249 divided by 1.249. Likewise, 3.749 divided by 1.49. okay, so we know this and this, of course it's just 1, so we're going to have 1, and then this value here, that's the denominator, into this value here, we are going to have what? 3. So in short, for this is representing what? Remember, this is sulfur and this is oxygen. So in short, we have for sulfur it's 1, and for oxygen it's what? 3. So the empirical formula for this, we are going to have for this sulfuric oxide, of course, is going to be what? Remember, sulfur is on 1 and then oxygen 3. So this is the empirical formula for this compound. This is basically how we go about it. Firstly, you have to write the percentages, or rather the masses that you have been given. Secondly, you have to write the relative atomic mass numbers. Third, you divide those same values. You divide the percentage given by the relative atomic mass number. Third, you divide the smallest value of whatever you have, and then you write your relative, rather the empirical formula. That's the way we go about this. Now, what is the molecular formula? So the molecular formula is the true ratio of atoms in a formula, often a whole number multiple of the empirical formula. Okay, you understand, don't worry when we look at an example. So for this one, the formula we use is simply the value of the empirical formula given. Okay, the empirical formula given, and then here we have n equal to relative mass number. So this is basically the formula. So the empirical formula that you have here, and then you find the value of n, and here you are going to be given rather the molecular mass number. So let's look at an example. Let's say we have been given that a compound has the empirical formula of, let's say, CH. So this is the empirical formula that we have, okay? And then the molecular mass of the compound is what? Let's say it's 78 per mole. Okay, so this is the relative mass number that we have been given. Then we have been asked to calculate the molecular formula of this compound, which of course is CH. How can we go about this? Okay, how can we find the molecular mass? Now, we have 78 here as the molecular mass. How can we find the molecular compound? So let's do this. So here we had said the empirical formula that you have been given, and then here the n equals to relative mass number. So the empirical formula that we have been given is what? CH. Okay, and then n here equals to molecular mass number that we have been given is 78. Right? So let's find the value of n. So in here we are going to calculate the relative atomic mass, or rather relative molecular mass, since we are going to add this, and rather this is a compound in short. So we are going to have for carbon, we know it's 1. There is only 1 carbon here, so it's just 1 multiplied by its relative atomic mass number of what? Of 12, plus for oxygen we have 1, and then we are going to multiply with its relative mass number, of course it's just 1, and then here we have n equals to 78. So let's look for the value of n. So in this case then, if we multiply 1 multiplied by 12, we are going to have 12, plus if we multiply 1 by 1, it's simply 1, and then here we have n equals to what? 78. Okay, so let's wrap the top part here. Okay, so make sure that you are writing all these. So now 12 added to 1 is what? Is 13. So we're going to have 13n equals to what? 78 here. So let's divide. So we're going to have 13 divided in there and 13 divided in there. So here we cancel, remain with n. And then 13 into 78 is what? Is 6 times. So the value of n in short is 6. Now remember, at first we had ch n equals to what? Equals to 78. So in this case, this side, okay, this side only is what represents the molecular formula. So in this case then, remember we have found the value of n, which is of course 6. If we multiply 6 throughout in here, we are going to have C6 and H6. So this is the answer to the question that we had. So hopefully that you have learned something today, and remember to like and subscribe.